Hey everyone, welcome back, and today let's solve Leetcode problem 2375 titled Construct Smallest Number from DI String. So we're given a zero-indexed string pattern of length n consisting of the characters I, that means increasing, or d, which means decreasing, meaning it is actually going to be a binary string where every single letter or every single element is either going to be an I or a d, where I would signify increasing and d would signify decreasing. Right now, a zero-indexed string num of length n plus 1, where n would simply be the length of the input string pattern, is created using the following conditions or operations. So num consists of the digits from 1 through 9, where each digit is used at most once. That is also very key to this problem's nature and properties. We can only use each element in the range from 1 to 9 exactly one time. Now, if pattern at index I is equal to an I, or increasing, then we know, following the property of an increasing sequence or list, num at index I would have to be smaller than the element to the right of it, or the next element at nums at index I plus 1. However, if the current pattern at the current index I is equal to a d, which signifies the decreasing property, that would mean that the current element nums at index I would have to be greater than the element next to it, or basically to the element right of it, which would be at nums at index I plus 1. Now we need to return the lexicographically smallest possible string num that meets these conditions, and that actually builds the possible string num that we form from the input string pattern. So in example 1, we have our input string pattern to be III, DI, and triple D. And in this case, we have an output of 1, 2, 3, 5, 4, 9, 8, 7, 6. Something very important to note is that the length of the input string pattern is going to have a length of 8, whereas the length of our output actually has a length of 9. Right, n would be 8 in this case, and we'd have an output to be string length n plus 1, or 8 plus 1, which would be equal to 9. And the reason why we do actually have these specific values at these specific indices in our output, for a quick explanation, at the indices 0, 1, 2, and 4, that means they're increasing. Because if you look at those indices 0, 1, 2, and 4, all of those indices or elements at those indices in the input string pattern are i's. Now, what do we know about the string or element I? It means that the current element at that index has to be increasing. And for it to be increasing, we know that the value at that index I has to be less than the value after it, right, directly after it. And you see that that does actually hold true for all the elements at those indices where the input string pattern is equal to an I, right? 1 is indeed less than 2, 2 is indeed less than 3, and 3 is indeed less than 5, and 4 is indeed less than 9. These are some very important observations to make in the problem's context here. We see that the output string at index 0, 1, 2, and 4 all have values that are less than the element after it, or directly to the right of it. And as per the indices that are decreasing at indices 3, 5, 6, and 7, all those values would have the d, or decreasing property, where the element after it would be less than it, right? And as you can see, 5 is indeed greater than 4, 9 is indeed greater than 8, 8 is indeed greater than 7, and 7 is indeed greater than 6. All of these values at those indices have that decreasing property. Now, the reason why we have an output of 1, 2, 3, 5, 4, 9, 8, 7, 6 is because we want to return the lexicographically smallest possible string num that meets these kind of properties or conditions from our input string pattern. There are several other kind of combinations of kind of strings that we could have chosen to still meet the criteria of using every single value in the range from 1 to 9 at most once from the input string pattern, and some of those possible other combinations would be this, or that, or even this. But the one that is the most lexicographically smallest is actually this. And what we really mean by lexicographically smallest is that we want to prioritize the smaller or smallest integers to come first, right? Kind of like how A, B, C, D, E, F, G works, where that would be lexicographically small, because we want the A, B, C, and so on and so forth values to come closer up, or to the beginning of this string, to make it more lexicographically small, right? Now, it also says that this wouldn't be a possible solution, although it is lexicographically smaller than our output, and the reason why is because we cannot use 1 more than once. That also applies to 2 and 3, or 4 even. We can't use multiple numbers in the range from 1 to 9 more than one time, meaning they can't have a frequency that's greater than 1. In example 2, we have our pattern to just be simply 3Ds. That basically just means that we want an output of length 4, which would basically be length 3 plus 1, and we want all of the elements to be in decreasing order, meaning every single element is going to be greater than the element after it. And the lexicographically smallest way to do this would be 4, 3, 2, 1. Notice how there are so many other patterns we could take. We could take 9, 8, 7, 6, or 7, 3, 2, 1, or even 5, 4, 3, 2. These all work, right? Because every value is greater than the element after it. But the reason why 4321 is the best output is, again, because it is the most lexicographically small. And the reason why is because we have the smallest values or integers in this output. 4, 3, 2, and 1, or 1, 2, 3, and 4, are the smallest values that we can have, and therefore it is the lexicographically smallest output that we can have as well. All the values in these other possible combinations have larger integers, which don't make them lexicographically small, at least in relative to this output, right? And that is going to be the smallest lexicographically possible number that still meets these conditions of having 3 decreasing values in the input string pattern. So for the constraints here, we see that the length of our pattern is ever going to be exceeding the value of 8, which makes sense because we can have at most length 9 input, or rather output, because of course we can only use all the integers from 1 to 9 at most once. And we're also given that the pattern is going to consist only of the letters I and D, meaning we're guaranteed that it is a valid input, it is a binary string, and we won't have to worry about any edge cases where we don't have valid inputs. Now that kind of leads us to the solution to this problem. How can we really solve this problem in a very efficient way while meeting the conditions and ensuring that our output string is as lexicographically small as possible? Well, that actually kind of leads us to our initial observation with the increasing and decreasing properties, right? And that observation is that whenever we actually encounter or whenever we see an I at any index in the input string pattern, we know that the next number has to be larger than the previous current one. And similarly, when we see the D, the next number should be smaller while also having the smallest possible values possible while keeping track and ensuring that those conditions are also met. Now, to actually construct this smallest number, we can use something called a monotonic stack, and we can use this stack to actually keep track of the digits while also maintaining the required increasing and decreasing order with the I and D inputs in the input string pattern. And the way we can do that, basically we iterate through the pattern and construct that result iteration by iteration or step by step, each value at a time. And the main idea of that solution is basically to push the numbers onto the stack whenever we encounter an I or increasing, and basically whenever we encounter an increasing, we want to then pop all the elements from the stack at that current iteration and then append them to the result. And that always makes sure that we have the smallest order. So now let's go ahead and get into the code here and see how that solution actually plays out and works in real time. So like I was just talking about, let's first initialize our stack. And I'm actually going to initialize it to something called the DQ, also known as a double-ended queue in Python. Now what a DQ really does, basically it stands for a double-ended queue. That basically it's basically going to store the numbers temporarily, and something cool about the DQ is that you can pop and append or push numbers from both sides of the data structure in constant or big O of one time, making it a very efficient data structure. And now once we actually initialize the stack, basically to store the numbers temporarily, let's get the result. And this is going to be initialized to an empty string. Why is it an empty string? Well, because we want our output to be in the form of an input or an output string pattern. And this is going to be the result that we effectively output once we're done building it from the elements in the stack temporarily whenever we encounter an increasing or I, right? That's going to store the final output that we effectively eventually return. So now let's actually build this result using the values from the input string pattern and building it as lexicographically small as possible. So first let's actually iterate through the pattern, and the simple way we can do that is basically for I in the range of the length of the pattern. But in this case, we want to go plus 1 because we do know that we want to have one extra digit in the output string, because we're given that the output string is going to have a length n plus 1, where n is the length of our input string pattern. Basically, we're iterating through every single character in the pattern, and we go one step beyond the length of the pattern. We need one extra digit for forming that smallest possible sequence. Now, in every iteration of this for loop here, so basically, okay, I think I missed a parenthesis, I'm not sure. I think I missed a parenthesis. Correct me if I'm wrong. I might get a syntax error after this. Okay, never mind. I did not miss a parenthesis. Okay, so for I on the iteration of length of pattern plus 1, in every iteration we want to append to our stack I plus 1, or the current index or element plus 1. And we want to do this in the form of a string because, of course, we want to output a string. So basically, we'll push or append to our stack.append the string, basically the string data type, converting the current element to a string of I plus 1, where I is basically the current index that we're at. Right, we're pushing for every single index I, we're pushing the next smallest number, basically I plus 1, onto the stack. And that always makes sure that we process the numbers sequentially. And the reason why we're pushing I plus 1, not like I plus 3 or I plus 100, because we want the smallest possible next number. And that would basically be the current element or index I plus 1, right? Kind of ensuring that we have the smallest number after the current element I, right? Now, what if in the current iteration or in the current index I, what if we've reached the end of the pattern? So meaning what if I is equal to the length of the pattern, it is the last element or the last index of the pattern, or we have currently an increasing element, or basically we want our current element to then be increasing. So if it's equal to the string I, or we've actually hit the end of the pattern, then we have to actually pop from the stack. This is a very key takeaway or key observation to make here. We have to pop from the stack and add it to our result while that's true. So if this is the case, while the stack is non-null, meaning while we still have elements in the stack to actually process, we'll actually add to our result or append to our resulting string the topmost element or recent most added element from the stack, and popping it off from the stack and adding it to the result, right, using the stack.pop method. Now, you may be a little bit confused on why we're doing plus equals. We're not actually adding a integer value to the result, right? The result is in form of a string, and since there isn't in Python, since there isn't really like a dot append or dot add method for strings to add elements to it, plus equals is the way that works to actually kind of simulate adding or appending a string to the result, and we're going to pop the topmost element from the stack and add it accordingly to the resulting string, and basically appending that value, right? So if this condition is met, meaning we've hit the end of the string, or the current element is actually supposed to be in increasing order, we then have to pop all the elements from the stack while it's non-null, and then append them to the result. And that actually makes sure, this is the key point here, that we're actually adding the numbers in decreasing sequence, right? We're actually all the numbers that we're adding that are in decreasing sequence, they're arranged correctly and sequentially. And effectively, once this is done, we simply return our resulting string. Basically, it's going to be the constructed resulting string. That would be the lexicographically smallest number that satisfied the given pattern of I's and D's. So unless I made any syntax error here, this should be accepted and there should be a valid solution. And as you can see, this really is just about as efficient as you can get. Very hard to beat this solution. So now let's kind of go back to how this solution works as a whole. Effectively, we iterate through the pattern or the input string pattern while also pushing every element or number at index I onto the stack. And whenever we actually encounter an I, or we reach the end of the pattern, meaning the last index of the pattern, we then have to pop all the elements from the stack that are currently in the stack at that iteration and then add them to the result accordingly. And that always guarantees that the sequence is actually going to follow the pattern while also making sure that we always have the smallest lexicographical order or sequence of values. So for the runtime complexity, it is actually going to be a linear time solution or a big O of n solution. Why? Because this really is just a single pass one for loop iteration solution. We're really just adding and pushing each number from the stack and to the string exactly once. That would be an overall linear complexity, and the memory or space complexity is also going to be linear or big O of 1 because we are actually using this input, or rather this extra auxiliary memory data structure stack, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.